The next speaker is Professor Bruno Martelli, who will talk about hyperbolic manifolds in dimension higher than 4. Let's welcome.
Okay, thank you. Thanks everybody for being here. This is going to be a hopefully gentle introduction to hyperbolic manifolds in high dimension. So let's start with definition. Definition. So I take a Riemannian manifold M, and I say that it is hyperbolic or flat or elliptic if it's locally isometric to one of the three most important Riemannian manifolds. So the three most important Riemannian manifolds are correspondingly hyperbolic space, Hn, Euclidean space, and the sphere. Okay, so another way to see this is that they have constant sectional curvature. So if and only if the sectional curvature, this is the sectional curvature, is everywhere. Everywhere means for every point and for every tangent plane at the point, equal to either -1 or 0 or +1. And we usually add some hypotheses. So we usually add completeness. So this is a very important hypothesis. Okay, so we usually suppose that manifolds are complete. And then we either study infinite volume ones or finite volume ones. So these are two different subjects. And okay, so today I will speak only about finite volume ones. Okay, so feel free to interrupt me and ask any kind of questions. Okay, at any moment. And so, for instance, if M is compact, of course it's complete and finite volume. But there are some cases where the manifold is complete and finite volume and is not compact. So the first thing to look for is examples. So okay, so there are examples in all dimensions. And you see from the very beginning that there is a striking difference between hyperbolic case and the other cases. So the first striking difference is that it is very easy to construct examples in these two cases. Like the sphere is itself an example of an elliptic manifold, and the flat torus with some flat metric is an example of a flat manifold. Okay, but it's not easy to construct examples of hyperbolic manifolds with this assumption, with finite volume and complete. Okay, that's the first important difference. So there are many such objects, but no one of them is really easy to describe. I think this is also, we are already facing a fundamental problem. A fundamental problem is there a way for every n to have a reasonable description of for instance, of a compact hyperbolic manifold? There are some descriptions, but they are not as immediate as these ones. Okay? So in one paper, Thurston wrote, he wrote many fundamental things, but he said that hyperbolic three manifolds are intrinsically three-dimensional. And that's true in any dimension. So a hyperbolic manifold of dimension n is something which is intrinsically n-dimensional. It's something that cannot be reduced to some lower dimensional things, as the torus can be. The torus is just a product of lower dimensional objects. The sphere is also somehow a join of smaller dimensional spheres. But this is never true for hyperbolic manifolds. That's why they're hard to describe. So the simplest way to describe them, and it's also the only thing that works in all dimensions, is to use arithmetic methods. So I'm not going to to explain what this means, I'm just going to show you one example. So the basic example is the following. You take a group, and as a group you take the intersection of the isometry group of the hyperbolic space, which is, so if you take the hyperboloid model of hyperbolic space, this is well known to be a very concrete Lie group, is a group of matrices preserving the Lorentzian N1 bilinear form. It's actually an index 2 subgroup in it, but this is not important now. And then you intersect it with, so this is a group of matrices. So you just take the integral matrices. You do a very naive construction. You just take integral matrices there. And you're wondering, are there really many integral matrices there? Maybe there are not so many. Actually, there are as many as enough to get a complete finite volume quotient. So the idea is that now I would like to take this. I quotient Hn by this group of integral matrices. It's not completely done because among these matrices here, you have some matrices that have fixed points. So this is not really a manifold. This is something which is called an orbifold. So actually, you don't really quotient by gamma. You quotient by some finite index group, finite index subgroup of gamma, which is always guaranteed to exist because these are matrices. Group of matrices always have finite index subgroups without torsion. So this in this way you get a manifold of this kind. Okay, and the arithmetic construction is just a variation of this. So it's a general definition that is valid for many Lie groups. But in this case, for instance, you can try to do the following variations. You could. So this is the group of matrices that preserve the form -1, 1, 1. They preserve the standard Minkowski bilinear symmetric form of this kind. And you could just vary some numbers here. You could put, I don't know, -3 here, -9, and intersect with the same group, and you get something else. Or you can put -√2, and then maybe instead of z here, you take all algebraic integers in the corresponding number field. Okay, so you do some arithmetic variation of this construction. And in this way, you obtain some class of manifolds that are called arithmetic of simple type, or simplest type. In even dimension, that's all. But in odd dimension, you also have arithmetic manifolds of some more complicated type that are constructed differently. Anyway, there are some general arithmetic techniques to construct examples in all dimension. And from these techniques, you immediately see some striking differences between hyperbolic manifolds and the other kinds of manifolds. So first of all, here, every elliptic manifold is covered by the sphere. And by Bieberbach, every flat manifold is covered by the torus. So in fact, there is only one commensurability class of elliptic manifolds and of flat manifolds. A commensurability class is just a very useful relation between manifolds. So we say that two manifolds are commensurable if they have a common finite cover. There is a finite cover for both. Okay, this is also a relation of subgroups of the geometry group of Hn. Okay, and here they are all commensurable. In fact, it's even more than that. They all have a common ancestor. So, and that's not the case here at all. So here we have infinitely many commensurability classes in every dimension. Infinitely many commensurability classes. Moreover, in every commensurability class, you don't have an ancestor like here. So every hyperbolic manifold is covered by some other hyperbolic manifold, which is topologically different from it, which is not the case for the torus. Okay, so you see immediately that there are more hyperbolic manifolds than any other kind of manifolds. Okay, but they are more complicated to describe, and that makes, of course, them more fascinating, right? And so let's see what we can do, so in lower dimension, of course, there's been a huge amount of literature about that. And let me briefly, is there any question about that? So these are just general definitions, but we already see something, in my opinion, that is very deep and interesting here. Okay. So the example we have here, okay, I forgot to mention. So there is also another striking difference between hyperbolic manifolds and the other kinds of manifolds, is that this is the only case where you can have manifolds that are not compact despite being complete and finite volume. For instance, this one is of this kind. This manifold here that I constructed before is of this kind. This means that in hyperbolic space, you can have cusps. So when you have a finite volume, complete hyperbolic manifold, you can have something called a cusp. So a cusp is something like this. So it's a topological end, which is just topologically like a product of some manifold T times 0 infinity, and T is a flat manifold of codimension 1. So for a surface, this is just a circle. But for instance, in dimension 3, this could be a torus. So you should think of a cusp as a flat torus shrinking exponentially fast. So it's a flat manifold shrinking exponentially fast. That's all. That's all it is. There's nothing hidden in this. Okay, and the metric is by some miracle hyperbolic. If you shrink a flat manifold exponentially fast with the good rate. Okay, so in particular, every hyperbolic manifold is the interior of a compact manifold with boundary, because you can attach a boundary at infinity. So all the manifolds I will speak today of will be either compact without boundary, or they will be the interior of a manifold with boundary, and the boundary is made of either of tori or of some more general flat manifolds. Okay? Is there any question? Okay, so let's see what happens very briefly in dimension 2 and 3, and then, so in the literature there are thousands of papers in hyperbolic geometry in dimensions 2 and 3, and only few in higher dimensions. So I will sketch what is known in dimension 2 and 3, and then I will easily summarize what is known in higher dimensions, since it's much less. Okay, so in dimension 2, so the general construction of a hyperbolic surface is the following. So you start with a right angle hexagon. Okay, so these objects exist in the hyperbolic plane. It turns out that the right angle hexagon is parameterized by the length of these three sides. So for every triple of positive numbers, there exists a unique hexagon. You take 2 copies of it, and you glue them along these sides. Yeah, so you glue 2 copies of it along these sides. And then what you get is you get something which is called the geodesic pair of pans, which is just made of two right angle hexagons. Now this is a closed geodesic of length 2b, 2a, 2c. So these 3 numbers are arbitrary. So here we have a similar theorem. So for every triple of positive number, there is a unique geodesic pair of pans. So it's a hyperbolic pair of pans where the boundary is a funny closed geodesic. And then you can take this as building blocks to build surfaces. So for instance, you can just double it. For instance, you can take this one, you do double along the boundary, and so you do something like this. You take 2 copies of it, and here you have the same curve as before of length 2a, 2b, 2c. And this is a genus 2 surface, hyperbolic surface. And you can get hyperbolic surfaces of any genus of greater than 1, so which is the same as the Euler characteristic is negative. So so this is a well-known construction, so you probably have seen it, but I want to recall it because this is in fact the only thing that works in high dimension. So the only topological constructions I know of hyperbolic manifolds in dimension higher than 3 are of this kind. So you start with a right angle object, So another striking fact in hyperbolic geometry is that there are plenty of right-angle objects. Okay, so even in hyperbolic plane, so in the Euclidean plane, you only have rectangles and nothing else. It's quite boring. In the hyperbolic plane, you have right-angle polygons with any number of sides from 5 to infinity. So and it's the same also in dimension 3. In dimension 3, you have. So in Euclidean space, the only polytopes with right angles are products of intervals. So cubes, just cubes. And here in hyperbolic space, you have plenty of right angle objects. For instance, you have a right angle dodecahedron or a right angle octahedron with points at infinity. In dimension 4, you have a right angle 120 cell. So it's a regular polytope in dimension 4 with right angle size. So you can mimic this construction effect. What I've done now is the only thing that really works in dimension at least higher than 3, which produces some topological object that you can investigate topologically. Okay. That depends on the parameters. So it depends very much on the parameter. Generically, no, because arithmetic surfaces are usually countably many. But here you have so in dimension 2, of course, dimension 2 is very peculiar. So in the fact that you can vary this parameter, and then you get infinitely many hyperbolic structures on the same surface. In fact, every hyperbolic structure on a genus G surface is constructed in this way. Every hyperbolic structure, and you have 6G minus 6 parameters. Okay, and the space of all the hyperbolic surface you get is called Teichmüller space. And it has a natural topology which makes it homomorphic to R to this 6G minus 6. So in particular, on a surface with negative Euler characteristic, you have infinitely many different hyperbolic structures. They all have the same volume by Gauss-Bonnet, but they are different. They are non-isometric, generically. But this is true only in dimension 2. Okay, so in dimension 3, okay, that's all I wanted to say about dimension 2. So if you have any questions about surfaces, that's all. So they can all be constructed in this way. You start with a hexagon, you double, and then you attach various spans like this.
Sorry.
Yeah.
There you have 3 parameters and G is 2.
Yeah, because at every curve you have a twist parameter. At every curve you have a 1 degree of freedom to grow to. This is only a very two-dimensional thing. This is not going to happen in higher dimension. Okay? So here, for instance, you have 6 parameters. In the sense you have the length of the 3 curves, and you have a less well-defined parameter, which is this 1 degree of freedom. It's not easy to fix the 0. Well, what is the 0 here? But you need, I mean, but there is 1 degree of freedom here, 1 here, 1 here. So you have 6 parameters. Any other question? Okay, so it's already a very nice theorem in hyperbolic geometry to show that every hyperbolic surface is constructed in this way. Now in higher dimension, so the situation, so usually the usual thing that we say is that the more we raise the dimension and the more rigid things become. So you have immediately more rigidity, you have most of rigidity, immediately. So most of rigidity says that the Teichmüller space of a higher dimensional hyperbolic manifold is the point. So if you take a manifold, if it has a hyperbolic structure, which is not always the case, if it has a hyperbolic structure, then it is unique. It has at most one hyperbolic structure. Of course, up to something, up to isotopy, up to homotopy. However, this is true in the strongest possible reasonable sense you can think of. Of course, it's not unique in a strict sense because you can perturb it using homotopy, but it's unique up to homotopy, up to isotopy. But it's really very, very strong. Okay, so the statement can be made very, very strong. Like every homotopic, like the strongest statement is that every isomorphism between the fundamental groups of two hyperbolic manifolds can be realized by a unique isometry. So that's a really strong statement. Okay, and yeah. Yeah, at most one. Okay, so let me. Okay, so in dimension 3, okay, so now dimension 3, of course, there is a fundamental contribution of Thurston. Okay, so until the 70s, there were some sporadic examples of hyperbolic 3 manifolds. Some of them were constructed from hyperbolic polyhedra, like the one I showed you before. You start with, I don't know, a dodecahedron with some nice dihedral angle, and then you glue the phases. Some sporadic examples of this kind. And then Thurston came and he showed that actually most 3 manifolds have a hyperbolic structure. And then he proposed the geometrization conjecture that was then proved by Perrin. So I will write both names. So what does this conjecture say? So the conjecture says that every 3 manifold so decomposes canonically so the decomposition is a typical cut and paste topological operation. So it's decomposed along spheres and tori. Every 3 manifold goes canonically into geometric pieces. Okay, so I'm supposing all manifolds are orientable during this talk. Otherwise, you should add Klein bottles here. And in the non-orientable case, actually, this theorem is not true. The non-orientable 3 manifolds are trickier. I mean, there are some issues there. But so let's stick on orientable ones. And so I'm not going to say what decomposing means. Okay, this was known already before Thurston. So there were some canonical decompositions available already in the 70s. It's like something like every integer decomposes into a product of prime numbers, something like this. And then you look at the prime numbers, and then the intuition of Thurston, proved by Perelman, was that those prime numbers are all geometric. So what do we mean by geometric? Geometric means they admit a locally homogeneous metric. So the metric is going to be complete and finite volume, like all the metrics we see today in this talk. So I'm not going to write it. This is always assumed. So the metric is going to be complete and finite volume. Locally homogeneous means that for every, so you have your manifold. For every couple of points in the manifold, you find 2 neighborhoods that are isometric. It means that all points look locally the same. There's a local isometry from this ball to this ball. Okay, and actually it turns out that the possible metrics you have in dimension 8 are only, they must belong to a finite list. So there are 8 possibilities, possible such metrics. And they can be described easily. So first the 3 constant curvature one, the sphere, Euclidean space, and hyperbolic space. Of course, these are the queens, the most important metrics in any dimension. And then you have some mixed metrics, like for instance, S2 times R, H2 times R, I'm not going to write R2 times R because it's already R3. Okay, but of course, these metrics are all intrinsically different. Okay, these are not, the sectional curvature here is not constant. These are homogeneous, but the sectional curvature is not constant. And then you can take any Lie group. If you take a Lie group, whenever you have a Lie group, you can always put a homogeneous metric. So, for instance, there are 3 Lie groups here. One is nil, one is sol, and one is SL2C. No, R. Okay. Okay, these are Lie groups. Okay, 3-dimensional Lie groups. Whatever they are, it's not important, but these are 3-dimensional Lie groups, and from a Lie group, you can always get just put any metric on the tangent space at the identity and then carry it by left multiplications everywhere. Actually, they don't really have a preferred such metric. You can choose any metric you want. Okay. So the theorem says that every after some decomposition, every 3-manifold decomposes into pieces that have one of these 8 metrics. And it turns out that the manifolds that you get from these 7 metrics were already known by Seifert in the 1930s. So Seifert didn't care about geometry, he only cared about topology. He just produced a list of manifolds that are called Seifert manifolds. Actually, these ones do not really belong to this list, but these are also very simple to classify, so I just include them. So these are manifolds somehow that all these 7 kinds of, no, sorry. Okay. So everything except hyperbolic manifolds is a Seifert manifold. And the Seifert manifolds are somehow manifolds that are, they are all bundles of, they all decompose. They all decompose somehow into, they are all 3 manifolds that decompose into a 2-dimensional manifold and a 1-dimensional manifold. They are all fiber bundles over 2-dimensional orbifolds. Or in this case, it's a fiber bundle over the circle. Okay, so you see that somehow hyperbolic manifolds, as I said before, they do not want to be reduced as a simple description of lower dimensional objects. So in particular, every manifold here has a name, has a well-established name. And we all agree on these names, more or less, except some parameters. But on the other hand, hyperbolic 3 manifolds don't have a name. They are not classified. They're extremely mysterious, and that's why people keep studying 3-dimensional topology, because we don't know how a random 3-manifold looks like. We know it's hyperbolic, but it doesn't mean that it has a name. It doesn't mean that they're not classified. Right? There are many of them. The geometry helps you a lot to understand the topology, but it doesn't help necessarily to classify them. There's no list. There is no dictionary of all hyperbolic 3 manifolds. Okay, so I want to stress this. The proof of this theorem does not imply that we have a satisfactory classification of hyperbolic 3 manifolds. Okay, so in particular, the most important result in hyperbolic 3 manifolds in the last 20 years is the following. Okay, so what is the So after geometrization, we understand that the most important 3 manifolds to look at are the hyperbolic ones. But we are still far from having a nice description of all of them. In particular, for instance, even a classification up to commensurability is out of reach now, as far as I know. So even if I want to classify them up to commensurability, I don't know, at least as far as I know, a nice classification of this kind. One step towards this direction is the following important theorem of Hegel. So Hegel proved that every hyperbolic 3-manifold virtually fibers. So what does it mean? So as I said, a hyperbolic manifold is usually very reluctant to be a fibration. So this is a very somehow paradoxical theorem. Okay, it is one of the discoveries is of Jurgensen and Thurston that there are many hyperbolic three manifolds that actually do something which is somehow counterintuitive. They do fiber over the circle. So some hyperbolic three manifolds are the total space of a fibration over the circle. This is the only way they can be a total space of some fibration. The only fibration they can have is over the circle. They cannot fiber over the surface. And this is somehow paradoxical for geometric reason, because the hyperbolic structure of the three manifold is, does not communicate very well with the structure as a fibration. If you want an example of this, think that if you have a fibration is something like this. Above every point you have a surface. And then you look at the pre-image of this surface. This surface is called the fiber. You look at the pre-image of the surface in hyperbolic three space. This is going to be a union of, it's a joint union of topological planes. But every single plane is embedded in H3 in such a complicated way that it goes to infinity by filling the whole sphere as a piano curve. So it's something that I'm not able to draw. Okay, it's a very distorted surface that reaches all possible points at infinity. So it's very far away from being totally geodesic. So in Riemannian geometry, if you have a codimensional manifold, maybe you hope that this manifold is totally geodesic. If the manifold is totally geodesic, then the pre-image in the universal cover is just something like this, something very simple. This is very far away from this. So the pre-image of this is a very crumpled surface, whose limit set at infinity is not a straight circle, it's the whole sphere. Okay, so it's hyperbolic manifolds are reluctant. They don't want to fiber, but somehow they do, nevertheless. And when they do it in a very strange way. Okay, so it's even more striking that they virtually all do. Virtually means up to taking a finite cover. So if you have a hyperbolic three manifold, maybe it doesn't fiber. Maybe simply because the first Betti number is 0. If the first Betti number is 0, it cannot fiber. But there is always a finite cover that fibers. So this is a very important theorem in hyperbolic geometry. Okay. Is there any question about that? So the proof is very long. And
is there any classification of the topology of the fibers?
Yeah, the fiber can be any surface of genus at least 2. So the fiber is any surface with negative.
So is there any corresponding theorem about knot complements?
Yeah, it's the same.
So any knot complement, any hyperbolic knot complement fibers?
No. Any hyperbolic knot complement virtually fibers. It means that it has a finite cover that fibers. Okay. Yeah. A knot complement can either fiber or it can. So the hyperbolic manifolds that, if you take a hyperbolic manifold, either it fibers or either it doesn't fiber. And it's a bit half and half. There are many manifolds of both kinds. But up to taking some cover, they all fiber. Is there another question? Yeah. If the first Betti number is at least 2, then by Thurston's fantastic theory of there is a norm on homology, and then you can perturb any fibration. In fact, you don't really need the Thurston theory there. So this is true in general. So this is true for any manifold of any dimension. So if you have a manifold of any dimension that fibers over the circle, if the first Betti number is at least 2, you can always perturb it and get fibrations that represent nearby classes. Okay, you don't really need Thurston's machinery. This is true in any dimension. You can perturb fibration. It's not very intuitive, but it is true. Any other question? Okay. Any surface of negative characteristic, yeah. So there's a theorem. Okay, here's the theorem. So the theorem is that you do the other way around. So you start with a surface. So the surface must be of genus at least 2. This is easy to prove. So the surface must have a negative Euler characteristic. So you start with a surface F with negative Euler characteristic. F can also have punctures, but you can stick to the closed case. Well, it's a genus G surface. Then you take a self-diffeomorphism of F, a self-diffeomorphism, and then there are three possibilities. This is also due to Thurston. It's very easy to quote people when you talk about these things. So there are three possibilities. So either phi is of finite order. Finite order means that there is some finite power of phi, which is isotopic to the identity. Or phi is reducible. Reducible means that it preserves a finite set of disjoint simple closed curves. So phi preserves us up to isotopy. Everything is up to isotopy. Preserves some, for instance, phi. So you think of phi. So what's the point? Why am I looking at phi? Because whenever you have phi, you get a three-manifold fiber ring over the circle, because you take the surface times the interval, and then you glue it back using phi, and then you get the three-manifold that fibers over the circle. And phi is called the monodromy. It's only important up to isotopy. So up to isotopy, it's either finite order or reducible. Reducible means it preserves some curves. For instance, it could preserve this pair of curves. Like phi sends this curve to this and this curve to this. Or it is pseudo-Nosov. So pseudo-Nosov, I'm lazy enough to say that as a definition, pseudo-Nosov is just if it's not finite order and reducible, as a definition, it's pseudo-Nosov. But of course, there is a clever definition. The clever definition is that it preserves something called projective measure laminizations. Whatever, this is the generic case. And then there is the theorem of Thurston is that in this case, so the manifold you get, you call it M5. In this case, the manifold is hyperbolic. In this case, it's not. So in this case, the manifold is hyperbolic. So whatever surface you have, you take a generic, in some sense, a generic self-diffeomorphism, and the manifold you get is hyperbolic. But generic doesn't mean that it's easy. So if you construct some simple kind of self-diffeomorphism, it's probably going to be of this kind. So to construct a pseudo-Nosov self-diffeomorphism, you need to do some work, right? So it's generic, but it's not easy to construct. That's the usual thing. Okay, is there any? And this is a strong theorem of Thurston. Okay, this geometrization in this case. So he proved geometrization for this kind of manifolds. Okay, so let's go to higher dimension. Okay, so now we go to dimension higher than 3. So the literature is not as large as in the previous cases. So it's easy to list more or less everything we know. And so I wanted to start with, so let's first talk about volumes. Okay, so remember that every hyperbolic manifold I'm talking about is complete and finite volume, which means either it is compact or it has some cusps. And so the first thing is that, so you have a theorem of Wang, that so for every possible V, there are only finitely many manifolds with volume smaller than V. So there exists a number, let's call it rho V, which is smaller than infinity, hyperbolic and manifolds with volume smaller than V. So n is fixed, okay? In everything I'm saying, n is fixed. if you vary n, then this theory is probably simply unknown. Okay, but let's fix n. So if you fix n, there are only finitely many manifolds of bounded volume. That's already a striking difference with dimension 3. So in dimension 3, there is a phenomenon called hyperbolic depth filling, which implies that you get infinitely many hyperbolic manifolds with volumes less than 5. Okay, but here you don't have this. So this is the number of hyperbolic manifolds in dimension n, okay, of volume less than v, and then you look at how this number grows, and then you have the theorem of Berger, Gelander, Lubowski. Moses. So this number grows more than exponentially. It grows roughly factorially. So rho v grows. It's between C2 and C1. So okay. So rho v grows like this. Okay. There's two constants. So it grows more than exponentially, but not much more. Okay. This is not a surprising theorem if you think about it, because. So the point is that this is the usual growth of graphs. So if you look at all graphs with bounded valence, and you count how many graphs are there, this is the number of graphs. And so in many cases, you can construct a hyperbolic manifold from a graph. So for instance, if you have a hyperbolic manifold like the one I drew before, a manifold with geodesic boundary. Hyperbolic manifolds with geodesic boundary exist in all dimensions. So if you take one of them and you glue many copies of it along a graph, you get more than exponentially many manifolds with bounded volume, assuming that the manifolds you get are all distinct, which is something you can believe, roughly.
Should we understand that most hyperbolic manifolds can be constructed from graphs?
No, this is unknown. Yeah, this is just unknown. Okay. I think there is a lot of dark matter, because the point is that there are hyperbolic manifolds that we can construct, and then there are many hyperbolic manifolds that we don't know if they exist. So for most hyperbolic manifolds, we know nothing. We are not able to construct them. So it's very hard to say most hyperbolic manifolds are blah, 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 because there is a lot of dark energy. So there are many of them probably we just don't see them. Okay. But there is also, so you remember in any dimension there are some hyperbolic manifolds that are called arithmetics. So arithmetic, those are the ones that you are able to construct using arithmetic method. So there is a paper of Bello-Lipetsky. How do I write it? Bello. So usually arithmetic hyperbolic manifolds are much less than the general ones. So for instance, here it's really striking difference. So the number of arithmetic ones, so I put arithmetic here. The number of arithmetic manifold grows roughly polynomially. Which is much less than this. Okay, so most hyperbolic manifolds are not arithmetic. That's already something. How do you construct non-arithmetic hyperbolic manifolds? So there is a construction of Gromov and Piatetsky-Shapiro. The GPS construction. The GPS construction is as follows. So you take two arithmetic manifolds. Arithmetic manifolds typically contain many totally geodesic hypersurfaces. So you take one of this kind, which contains a totally geodesic hypersurface like this, and you take another one, which is a very different kind from this one. In particular, they are not commensurable. It is easy to check commensurability using arithmetic methods. It amounts at checking whether some bilinear forms are isomorphic or not. So it's just simple arithmetic. So suppose you have two non-commensurable hyperbolic manifolds that share the same codimension 1 totally geodesic manifold. So this totally geodesic manifold is the same. This also can be done using arithmetic methods. It's a bit like taking the same bilinear form and extending it one dimension higher in two different ways. So it turns this becomes simple algebra. And then what you can do is that you can glue 1/2 of this to 1/2 of that. And this, by some general reason, is not going to be arithmetic. Okay. So in particular, using this construction, you can do this construction with graphs, as I did. You take manifolds that are not commensurable and you glue them all together. You can do graphs of non-arithmetic manifolds. And using these techniques, what are the names? So Gelander and Levitt. Yes. So they prove that even the commensurability classes of non-arithmetic manifolds are much more than the arithmetic ones. So even if you quotient hyperbolic manifolds by commensurability class, you still get the same growth for the non-arithmetic ones. Okay. So same growth, this growth here. Same growth for commensurability classes. This is a strong theorem. So you count commensurability classes up to with bounded volume, and they still grow more than exponentially, despite the fact that the arithmetic ones, they don't grow, even without considering commensurability classes. They grow only polynomially. So this shows even more that non-arithmetic manifolds are more frequent than arithmetic ones, but this is more or less the only technique we know to construct non-arithmetic hyperbolic manifolds. There is also another technique which is starting from Coxeter polytopes. So there are only two techniques to construct non-arithmetic hyperbolic manifolds. One is to cut and paste along totally geodesic surfaces like here. And another one is to start with some Coxeter polytope which is known to be non-arithmetic by a criterion found by Wimberg. But these Coxeter polytopes, they exist only up to some limited dimension. Okay, so this is the only technique that works in any dimension. So maybe, as I said before, maybe there are many hyperbolic manifolds that are not of this kind, and we just don't see them. Okay, so we just don't know. Okay. So what about minimal volume ones? So the Radcliffe, Chance, and some co-authors. So they found some minimal volume ones in low dimension. So first, let me say one thing. So if n is even, then the volume is proportional to the Euler characteristic via a constant which only depends on n. This is a generalization of Gauss-Bonnet. So when the dimension is even, the only thing that matters is the Euler characteristic. The Euler characteristic is negative if the dimension is 2, positive if it's 4, negative if it's 6, and so on. So in particular, they found some minimal volume manifold because they found that they have Euler characteristic 1. And so in dimension 4 and 6, there exists some hyperbolic manifold of minimal volume which is known because the Euler characteristic is plus or minus 1. So it's plus 1 in dimension 4 and minus 1 in dimension 6. And they build these manifolds using right-angled polytopes, which are the only tools I know to do some topology with hyperbolic manifolds in higher dimension. And they also have a candidate for n equal 5, but in n equal 5, the volumes are not, they are discrete, but they are not as simple as that. So this is very simple because it means that volumes are somehow a subset of the integrals of this content. constant. On the other hand, the volume of 5-dimensional manifolds, they form a discrete set, but we really don't know. We know nothing about this set except the fact that it's discrete. So it's not easy to find the minimal volume one. There's a candidate. Okay, so all these manifolds are cusped. So in the compact case, in dimension 4, there is one example with Euler characteristic 8. And we don't know if there is some smaller one. And okay, let me mention briefly. So another thing you can look at cusps. So there are cusped hyperbolic manifolds in no dimension, but here you see another important fact. So the important fact is that there is a theorem of Stover that in the arithmetic case, the situation is very. So in the arithmetic case, for every C, there is a dimension n, such that there are no hyperbolic manifolds with at most C cusps when the dimension is bigger than n. So such that there is no arithmetic manifold Mn with Mn, so n0 here, Mn with at most C cusps. So in the arithmetic case, the higher the dimension is, and the higher the number of the cusps must be. So in particular, so there are only, we don't know. That's all we know, more or less, except that in dimension 4 we know that. So there is a theorem I proved with Kolpakov. So in dimension 4, you can find manifolds with any number of cusps. In particular, there are manifolds with one cusp. Okay. So in dimension 4, so there are some 4 manifolds with any number. But for instance, we don't know if there exists a 5 manifold with one cusp. We know there is an example with 2 cusps, but not with one. And no. Okay. And another funny thing is that, so there's another theorem in dimension 4, which is nice, I like to. So there is a paper of Long and Reed. So the 4-dimensional world is peculiar. So if you take a hyperbolic for manifold, so in general, so there are some general things. So if you, I will write them down, but they are not proved by them. So if you take a hyperbolic for manifold, then what do you get? So you can write it this way. So if you take a hyperbolic for manifold, then the signature of the manifold is going to be the eta invariant of the boundary. So the boundary of a cusped for manifold is a union of flat manifolds. And there is some mysterious invariant, mysterious for me, invariant called the eta invariant. And this equals the signature. I don't know if there's a sign, maybe there's a sign here, I don't know. In particular, this generalized the well-known theorem that if the manifold is closed, then the signature is 0. This is a consequence of Hirzebruch formula in dimension 4. But there are examples where the manifold is cusped and the signature is non-zero. But these were recently constructed. So in the cusped case, you can have non-zero signature. This also implies that among the 6, so there are 6 flat 3 manifolds, and only 3 of them can arise as the boundary of a hyperbolic for manifold with a single cusp. Because among the 6 flat 3 manifolds that we have, only 3 of them have the Euler number, which is an integer. Because this Euler number is sometimes not an integer, while this is always an integer. Okay, so and for one of them we still don't know. So there is a very nice compact flat 3 manifold called the Hansch event, and we don't know if there is a hyperbolic 4 manifold with a single cusp, which is the Hansch event. We know that there are some with 5 cusps, and they are all the Hansch event, but not with one. Okay, so yeah, and enough for the cusp. So I will finish by saying something about the topology. So I will state a couple of theorems. So one is So the last two theorems I'm gonna state show the striking difference between arithmetic methods and the non-arithmetic methods. So using arithmetic methods, you can get many geometrical useful information. For instance, there is this very nice theorem proved by Bader, Miller, Fisher, and Stover. Okay, this is a very, really a great theorem because it's easy to state also. And so if you have a hyperbolic manifold, and suppose that the manifold contains infinitely many immersed, totally geodesics hyperbolic submanifolds of dimension at least 2. So I'm not considering just geodesics. Geodesics are not allowed. So suppose you have a 5 manifold which contains infinitely many totally geodesic immersed surface. Here I mean that the totally geodesic submanifold must be completed in finite volume. Okay. So then it's arithmetic. I think this was unknown even in dimension 3, and this is okay. So the non-arithmetic manifolds cannot contain infinitely many totally geodesic immersed submanifolds. Okay. So as you see, using arithmetic methods, you get plenty of power for things like this. On the other hand, if you want to study the topology, the arithmetic methods are not very good. So for instance, do we know the Betti numbers of some higher dimensional hyperbolic manifolds? Not so much. So for instance, the first theorem is the only one that uses arithmeticity, is a theorem of Milson of 76, which says that in any dimension there is a hyperbolic manifold with positive first Betti number. This is not complicated, no? Because if you have a totally geodesic non-separating surface, you're done. So it's not something really complicated to think of. But that's all we know. So using arithmetic methods, we cannot go much further than this. For instance, can we compute the second Betti number of some hyperbolic manifold? So the only manifold, so there is a paper I wrote with Italiano and Migliorini. So there are some examples up to dimension 8 where we can compute all the Betti numbers. Examples: M4, M8 with known. So computing the Betti number should be the first thing you do when you have a topological space, right? So up to dimension 8, there are some examples where we can do, and these numbers are huge. So in dimension 8, these numbers are 50 million, 40 million. Okay, so huge numbers. Even the Euler characteristic of this manifold is huge. And everything gets complicated if you raise dimensions. So the combinatorics is naturally complicated. Things are still human in dimension 4 and maybe 5, but then you get crazy. And then maybe the other, so another theorem we proved with the same collaborators is that there exists the hyperbolic 5 manifold that fibers over the circle. Okay, so this means that this is also a topological result. So these are both topological. All these results are topological. So, and all these things are obtained using right-angle polytopes. So like the hexagon, some higher dimensional version of the hexagon, something you can really work with topologically. Okay, so you see maybe in this blackboard what is the difference. So there are really 2 different ways to go to the same peak of the mountain. And here it's using arithmetic methods, you can compute many geometric things like the systole of the manifold or the commensurability class or the cusp shapes. You can do many things. If you want to compute Betti numbers, you're stuck. And the only thing you can do is just to try to use these polytopes, but these polytopes exist only up to dimension, they are known only up to dimension 8, and they do not exist if the dimension is higher than 15. So you can construct high dimensional manifolds, but not very high dimensional manifolds. Okay, and, I will stop here. Thank you very much.
So questions or comments?
Do the polytopes exist in dimension 3?
Yeah, there are plenty of them. There is a theorem of Alexander Riemannian. So if you have a combinatorial polytope and you look at it, and there are some combinatorial conditions, if these conditions are satisfied, then you can realize it as a right-angled polytope. For instance, the dodecahedron can be realized in a compact version, and the octahedron can be realized in an ideal version. So there are many of them.
So as hyperbolic.
Hyperbolic, yeah.
I see.
Yeah, the plan. This is a theorem which is this is a theorem of Andreev. Also, the proof of Andreev is I don't know. I've been told that it's not completely correct. That it was written again by somebody else whose name I forgot. So okay, but yeah, exactly. Yeah. Thank you. There's a very nice paper, right? So anyway, the paper of Andreev, I haven't read it. This one is very clear, and they prove this very nice theorem about three-dimensional polynomial.
Are there any constraints on the cohomology ring or of hyperbolic manifolds?
Okay, so
4 or higher?
Yeah, for instance, no, not that I know, except some sporadic cases, like for instance, so the Pontryagin numbers are 0 because this is true for every conformally flat manifold. So the Pontryagin numbers are 0, and this implies that the signature is 0 in dimension 4. In the closed case, in the Caspet case, it is not true. For instance, only recently we know that there are some compact hyperbolic form manifolds that are not spin, so with odd intersection form. This is just recent. So I don't know, for instance, if there is any hyperbolic manifold which is not the boundary of the topological manifold. So which is not in the trivial class in the cobordism group, for instance. In dimension 4, this is impossible because the signature is 0. But maybe in dimension 5, since there are only 2 classes, and I don't know if there are hyperbolic manifold in the non-trivial class. So I don't know any restriction, except that the Euler characteristic is in even dimension must be positive or negative according to.
More questions?
I just want to return first to the question about manifold which fibers, well, 3 manifold which fibers. Actually, no. Let me first ask about this result because it's right there. I think I saw a result earlier this week where it doesn't start off assuming that M is hyperbolic, but it just goes M is negatively curved, and there are infinitely many totally geodesic.
This one?
Yeah, maybe codimension 1 for that result. Then yeah, exactly.
Yeah, but
yeah. So I'm just asking, does M have to be hyperbolic for this result?
So it must be. So if the conclusion is arithmetic, then you must start with some kind of symmetric space, some geometry that arises from some Lie group. It cannot be an arbitrary negative curvature thing, because otherwise.
I understand that. I just mean like that result was saying if you start off with a negatively curved Riemannian manifold which satisfies certain conditions, then it is both hyperbolic.
That's their question. That's a different topic.
No, but I'm asking if this. Yeah, no, it's related to this question. I mean, this result. I'm just asking if you feel that it's possible to have this type of result, but not assume that M be hyperbolic in the first place, but then to deduce that it's hyperbolic in the process.
I don't know. Anyway, if you start with a hyperbolic manifold of this kind, I don't know.
I think so. The talk, there was a talk by CN City.
Yeah.
I think there was 4 authors as well, maybe.
Okay.
But the assumption is that M is only a closed hyperbolic negatively curved manifold.
Negatively curved. Yeah.
And, but then the assumption is slightly stronger that you have infinitely many immersed or totally geodesic hyperbolic submanifolds of codimension 1.
Okay, that should cover everything.
Yes,
Yeah.
and then
Otherwise,
it still gets that it's not
okay.
only symmetric,
That's reasonable.
but arithmetic.
Yeah, that's reasonable.
Okay, and also for the Gromov construction where you're pasting along geodesic boundaries, I think like in dimension 3 there are constructions where because we have enough control over the boundary character varieties, we have enough understanding of boundaries of 3 manifolds with non-toric boundaries that you can piece together things which are not totally geodesic. Now, a priori, this idea shouldn't work in higher dimensions because of Mostov rigidity, but is there an attempt to sort of study hyperbolic 3 manifolds and 4 manifolds with singularity and trying to see if there are ways of doing the character variety for boundaries of hyperbolic 5 manifolds, and then to cut along those and then glue along the singularities and hope that
I don't think there is almost nothing known about character varieties of boundaries of hyperbolic 4 manifolds in general. Even SL2C character varieties. So I don't think we know.
Okay, since the time is limited, so let's thank our speaker again. 对，我以前很早以前听过您的课。